Hello, everyone. Today, I am excited to introduce you to real-time operating systems. In this session, you'll gain a clear understanding of the Realtek BLE SoC SDK solution, and also acquire knowledge about two widely used RTOS, FreeRTOS and Zephyr. Let's take a look at our agenda. We'll start with an overview of RTOS, then dive into Realtek's OS interface, known as OSIF. Following that, we'll explore two popular RTOS options, FreeRTOS and Zephyr. Finally, we'll wrap up with some concluding thoughts. Let's begin with an overview of RTOS. So, what exactly is an RTOS? It's an operating system specifically designed to manage hardware resources and execute tasks with precise timing. Some key features of an RTOS include real-time task scheduling, which ensures tasks are completed within defined time limits. They also offer low latency and high predictability, providing consistent and reliable responsiveness. Additionally, RTOS is known for efficient resource management, maintaining low overhead for better system performance. You might be wondering, why should I use an RTOS? Well, there are several compelling reasons. RTOS enhances reliability and stability in your systems. It is optimized for tasks that require precise timing, which is crucial in many embedded applications. Lastly, it facilitates modular design, making your code easier to write and maintain. Now, let's talk about Realtek's OS interface, which is the RTOS solution of Realtek BLE SoC. So, what is OSIF? It's an abstraction RTOS layer provided by Realtek, designed to allow applications to run on different RTOS without modification. OSIF consists of 8 fundamental components: task, schedule, message queue, synchronization, timer, memory, pool, and list queue. We'll be diving into more details about these in the upcoming slides. If you're wondering how to use OSIF, the OSIF API reference is available online at our website, RealMCU. For those who prefer offline access, you can find the documentation in the doc directory of the SDK. We will focus on OSIF task first. The OSIF task provides capabilities for defining, creating, and controlling tasks to effectively manage their lifecycle and execution. OSIF tasks can exist in 4 states. The running state is unique, only one task can be in this state at a time. Ready tasks are prepared to run and are waiting for their turn based on priority. Waiting tasks are awaiting specific events before they can proceed. Finally, inactive tasks are either not yet created or have already terminated, thus using no system resources. The task priority range for Realtek BLE SoC is from 0 to 6, with 6 being the highest, except for the RTL8762C, which ranges from 0 to 4. Limiting the number of priorities brings 2 major benefits: reducing RAM usage and simplifying scheduling. Additionally, preemptive scheduling is used by default. Now, let's dive into the OSIF task APIs. To manage tasks, we have OS Task Create to create and initialize a new task. When creating a task, it's critical to define an appropriate stack size to ensure safe context switching. Next, we have OS Task Delete to remove tasks from active states and frees up the resources they were using. OS Task Suspend temporarily halts one task execution. Once suspended, a task cannot be scheduled until another task calls OS Task Resume to remove the suspension. If you want to trigger a context switch, there's OS Task Yield to transfer control to the next ready task. What's more, OS Task Handle Get would help you to get certain tasks handle. To manage task priority, we have OS Task Priority Get and OS Task Priority Set to enable you to obtain or adjust the priority of a specific task. Lastly, we have OS Delay. This function pauses the current task for a specified duration in milliseconds. It's a fundamental tool for creating precise timing in your applications. Let's move on to OSIF Schedule module. The scheduler is a core component of any RTOS, and OSIF provides a robust interface for managing it. Its design intent is to provide multitasking capabilities and to track system time effectively. Now, let's look at OSIF schedule APIs related to scheduler control. First, we have OS Sched Start to initiate the RTOS kernel scheduler, enabling multitasking. It's typically one of the last things you'll call in your initialization code before your application starts running properly. On the flip side, we have OS Sched Stop to halt the scheduler, deletes all tasks, and stops multitasking. It's not commonly used in most applications, but it can be useful in certain scenarios, such as when you need to perform a system reset. For scheduler suspension and resumption, we have OS Sched Suspend and OS Sched Resume. The suspend function blocks context switches but still allows interrupts, while the resume function restarts normal scheduling operations. To check the scheduler's state, you can use OS Sched as Start to verify if the scheduler is active, and OS Sched State Get to retrieve its current state. For system timing, OS SysTime Get provides the elapsed time in milliseconds since the scheduler started. Similarly, OS SysTick Get gives you the elapsed time in OS ticks. These functions are practical for precise timing in your applications. Let's move on to OSIF Message Queue. This is a crucial component for inter-task communication in RTOS environments. The primary functionality of OSIF Message Queue is to provide a communication mechanism between tasks and interrupts. It operates on a first-in first-out (FIFO) basis, ensuring orderly message processing. A key feature of message queues is their ability to facilitate data transfer and synchronization. They can block receiving tasks until messages are available and block sending tasks until there is space in the message queue. Now, let's look at some important OSIF Message Queue APIs. For queue management, we have OS Message Queue Create to initialize a message queue with storage allocation, and OS Message Queue Delete to remove a queue and release its memory. For message operations, OS Message Send appends an item to the end of the queue, while OS Message Rec extracts and removes an item from the front. OS Message Peek allows you to view an item at the front of the queue without removing it, but remember, this operation requires an adequately sized buffer. Finally, for queue insights, OS Message Queue Peek lets you check the number of items currently in the queue. Let's move on to the OSIF synchronization. The primary purpose of this module is to facilitate seamless communication between tasks or interrupts. The design goal is to ensure the safe access of resources that are reused serially. OSIF synchronization offers several key features. Firstly, the lock component ensures exclusive access to a resource. It does this by managing task preemption and interrupts effectively. Secondly, we have Semaphore, which manages the usage count of a resource. This allows multiple tasks or interrupts to access it without conflict. Lastly, the mutex provides mutual exclusion, a critical feature for protecting shared resources from concurrent access. Moving to OSIF synchronization APIs, the functions OS Lock and OS Unlock are designed for managing critical regions by disabling and re-enabling preemption and interrupts, respectively. For semaphore operations, with OS Sem Create, you initialize a counting semaphore, while OS Sem Delete allows you to delete a semaphore, freeing its resources. OS Sem Take and OS Sem Give are crucial for controlling the availability of a semaphore, allowing tasks to perform take and give operations effectively. For mutex operations, by using OS Mutex Create, you can establish a mutex, and OS Mutex Delete will let you delete one, releasing associated resources. Furthermore, OS Mutex Take and OS Mutex Give manage the locking and unlocking processes, ensuring that resource access remains organized and conflict-free. Let's introduce the OSIF timer module, which focus on efficient timer creation and management within a system. The design goal is to provide precise time management, enhancing operational flexibility for various applications. There are two primary types of timers. The one-shot timer, which triggers a callback once after a specified duration. The periodic timer, which triggers a callback at regular, fixed intervals. Timers have distinct states. Dormant is the initial state upon creation, where the timer is stopped. Notably, a one-shot timer expires at this stage and doesn't restart automatically, is also in dormant state. Active indicates that a timer has started or restarted, and it will trigger the callback upon expiry. Then, let's talk about the OSIF timer APIs. For managing timers, OS Timer Create is used to initialize a timer, allocate necessary resources, and provide a reference handle. With OS Timer Start, you can activate a dormant timer or reset it if it's already active. OS Timer Restart lets you alter a timer's period and restart it, activating it if it was previously dormant. To stop a running timer and move it to a dormant state, you utilize OS Timer Stop. Finally, OS Timer Delete allows you to remove a created timer permanently. Regarding timer information, OS Timer Dump outputs detailed timer information, while OS Timer State Get retrieves the current state, active or dormant. OS Timer ID Get is to get the unique identifier assigned at its creation. Next, we'll explore the OSIF memory module. Its primary function is to provide efficient management of heap operations, ensuring that dynamic memory handling remains both efficient and safe. When discussing RAM types, it's important to note that Realtek BLE SoCs utilize different RAM types for heap management. You can consult the memtypes.h file in the SDK to determine which RAM types are available for heap allocation. For a deeper understanding of the memory systems in Realtek BLE SoCs, I recommend visiting the memory section of the online documentation on RealMCU. Now, let's look at the OSIF memory APIs. For memory allocation, OSMEM-alloc is used to allocate a block of memory of a specified size. OSMEM-alloc not only allocates memory but also zero-initializes it. If specific alignment is required, OSMEM-aligned alloc is available for allocating a memory block with precise alignment. For memory freeing operations, OSMEM free releases an allocated memory block, while OSMEM aligned free is for freeing memory that was allocated with specific alignment. OSMEM peak allows you to view the total unused memory size for a particular RAM type, which is crucial for efficient resource management. Next, we will focus on OSIF Pool, which provides task-safe, fixed-size memory blocks for developers to use. The design intentions are to offer faster operations compared to dynamic heap allocation and to eliminate fragmentation issues. Some of the key features include a 3-layer structure where each pool can have multiple slots, with each slot managing buffers of the same size. There is also extended pool support, which facilitates the addition of new slots to existing pools to expand memory capacity. Furthermore, self-descriptive memory ensures that each memory block records a pointer to its own buffer at the beginning, which means no additional parameters are needed when freeing memory. To maximize performance and minimize fragmentation, we strongly recommend using exponential step sizes, e.g., powers of 2, for slot buffer sizes. This strategy optimizes memory utilization, allocation speed, and alignment while allowing dynamic expansion. For specialized scenarios, e.g., frequent mid-size objects, adjust the step strategy, e.g., hybrid steps, as needed. Now, let's look at the OSIF Pool APIs. For pool management, OS Pool Create is used to create and initialize a memory pool. With OS Pool Extend, you can add additional slots to an existing pool, giving it greater flexibility. If you need to remove a pool, OS Pool Delete is the function to use. For buffer management, OS Buffer Get allocates a buffer from a pool, while OS Buffer Put returns a buffer back to the pool, maintaining balance and resource availability. Finally, OS Pool Dump allows you to display the buffer contents of a memory pool, providing insights into memory allocation and usage. Okay, let's come to the last module, List Queue. As a queue structure, it implements basic first-in first-out (FIFO) operations, including in-queue, dequeue, and peek. Additionally, List Queue provides extended operations such as inserting and deleting elements at any position in the queue. List Queue enhances task scheduling and improves the efficiency of real-time processing. Now, let's delve into the List Queue APIs. For initialization, OS Queue init is used to set up and initialize the list queue, preparing it for use. For queue operations, OS Queue in appends an element to the end of the queue, while OS Queue out is used to take out the first element from the queue. For inspecting the first element without removing it, OS Queue peek comes into play. OS Queue insert allows you to add an element after a specified position within the queue. Finally, OS Queue delete removes an element from the queue. At this point, the content of the 8 components of Realtek OS interface has been fully introduced. Next, we will introduce FreeRTOS. Starting with its core features, FreeRTOS is known for its lightweight and simple design with extensive chip support. It's MIT licensed, ensuring that developers have access to a permissive, open-source licensing model. And we have 3 reasons why Realtek BLE SoCs are highly compatible with FreeRTOS. First, native integration. FreeRTOS is natively integrated into the ROM of Realtek BLE SoCs, which allows for a seamless and efficient operating environment. Second, the OSIF module is set to connect with FreeRTOS by default on these SoCs, ensuring smooth handling of tasks and operations. Third, proven stability. FreeRTOS has been extensively validated on Realtek BLE SoCs, providing exceptional stability and reliability for developers and end users alike. When you use the OSIF FreeRTOS version on Realtek BLE SoCs, there are some important points to take care of. For example, in FreeRTOS, scheduling begins only after OS Sched start is called. And FreeRTOS's timer callback is executed in a timer task with highest priority. Now, let's talk about Zephyr OS. Zephyr is known for its highly configurable and modular design, which provides great flexibility in tailoring the operating system to specific needs. It comes with an extensive HAL, making it easier to work across different hardware platforms. With strong community and enterprise support, Zephyr offers a reliable ecosystem for developers. Zephyr supports native development on Linux, Mac OS, and Windows. It is licensed under Apache 2.0, ensuring a permissive, open-source licensing model. Talk about Realtek's support on Zephyr. Currently, the RTL8752H and RTL87X2G series SoCs support Zephyr. In the future, Realtek plans to extend Zephyr support to more series SoCs. Developers can access the Realtek Zephyr SDK from the connectivity, which is the Realtek's GitHub server. Additional Zephyr development resources and documentation can be found within the Zephyr project documentation. Zephyr OS provides a complete development platform. The diagram on the right shows the architecture of Zephyr. Above the hardware platform layer, we have the HAL, which provides compatibility across multi-vendor SoCs. The architecture interface layer ensures that platform-specific capabilities are efficiently managed. At the core, we have a lightweight kernel. Despite its small size, it is scalable and provides essential features. Moving up, the OS services layer offers diverse services including device drivers, storage and security services, as well as logging, tracing, and debugging tools. Before the final application layer, we have connectivity layer. You will find that Zephyr is highly connected, offering support for Bluetooth 5.0 and BLE, Wi-Fi, Ethernet, CAN bus, and various IoT protocols like OpenThread and Mesh. It also supports USB and USB-C, ensuring broad connectivity options for developers. This architectural design makes Zephyr an excellent choice for developing complex, interconnected systems across various hardware platforms. When you use the OSIF Zephyr version on Realtek BLE SoCs, there are also some points you need to note like FreeRTOS version. For task module, OS task create is implemented by calling kthread create. It is important to note that we set the parameter delay of kthread create to 0 by default, which means that after calling OS task create, the created task will be immediately added to the schedule. Talk about timer module. Zephyr's timer callbacks are executed within the system timer ISR. Hence, it's crucial to avoid any time-consuming operations within the timer callback to prevent interrupt overruns and ensure system responsiveness. Here comes to the conclusion part. Let's summarize today's 3 takeaways. Firstly, OSIF provides a unified RTOS abstraction layer that supports compatibility across multiple RTOS environments. It comes equipped with a comprehensive API suite, helping you to efficiently leverage kernel services. Secondly, FreeRTOS is native integrated with Realtek BLE SoCs, and OSIF FreeRTOS version has been proven to offer exceptional stability and reliability. Lastly, Zephyr is a highly modular and configurable RTOS solution that's continually evolving, with expanding support for the Realtek BLE SoCs. Backed by a strong community and solid enterprise support, it represents a robust platform for modern development. In summary, these components provide a powerful, flexible, and reliable foundation for your next project. Thanks for your listening.